Look at a modern reservoir, and you're looking at trillions of gallons of water held in suspension above human cities. If the structure holding it back experiences a single point of failure, that suspended ocean becomes an erasure mechanism for everything downstream. The continuous threat trying to cause that failure is the water itself. It exerts a staggering, constant weight against the structure, a force engineers call hydrostatic pressure. This diagram shows exactly how that pressure behaves. Because water has mass, pressure increases linearly the further down you go. The water at the bottom crushes against the wall with far more intensity than at the surface. Because of that uneven distribution, the total sum of that crushing force converges at a single mathematical point. Engineers call this the center of pressure, and it sits exactly 2/3 of the way down the wall. If you put a standard flat concrete wall in front of that concentrated force, the water will do one of two things. It will either push the entire structure horizontally across the bedrock, causing it to slide, or it will simply tip it over. Holding back millions of tons of deep water requires highly specialized structural geometry. A modern dam is an engineered machine that uses exact combinations of mass and shape to neutralize specific mechanical attacks. The most straightforward architectural defense against the water's crushing weight relies on sheer, overwhelming mass. Looking at this force diagram of a gravity dam, you can clearly see the mechanics. The immense downward weight of the concrete itself generates enough friction against the ground to completely resist the horizontal force of the water pushing forward. To generate that kind of friction, you need a structure on the scale of the Grand Coulee Dam, a solid pyramid of concrete so heavy that the river behind it simply cannot push it out of the way. You can achieve a similar effect without concrete. Embankment dams swap cement for millions of cubic yards of compacted earth and rock, stacking material wide and high to form an impenetrable artificial mountain. Both designs conquer the hydrostatic threat by turning raw geological weight into an immovable anchor. But you cannot build a massive, wide-footprint gravity dam inside a steep, narrow canyon. There simply isn't enough physical space for the footprint required. This is where engineers rely on the arch dam. Instead of a thick pyramid, the face of the dam is a relatively thin wall that curves directly into the body of water. The mechanics of this curve are incredibly efficient. When hydrostatic pressure pushes against the face, it squeezes the arch tighter, making the concrete stronger. Instead of using sheer mass, the arch takes the forward force and channels that load laterally, straight into the solid canyon walls. In extreme environments, engineers combine both strategies. The Hoover Dam is a hybrid arch gravity megastructure. It relies on 6.6 million tons of concrete weight, but it's also curved to actively manage up to 45,000 pounds of pressure per square foot. By utilizing the water's own crushing power to physically lock the dam into the earth, the arch design replaces brute force with structural mechanics. Managing static pressure only solves part of the equation. Dams also face dynamic threats, particularly massive seasonal floods that cause water levels to rapidly rise over the crest of the structure. To prevent structural failure from overtopping, engineers install spillways and penstocks. These systems function as giant pressure release valves, safely bypassing excess water around the dam entirely. The scale of this hardware is immense. At the Hoover Dam, the spillway systems capture floodwaters and force them into 50-foot-wide concrete-lined tunnels, dropping them a sheer 700 feet into the river below. During a flood event, water accelerates to 120 miles per hour inside these bypass tunnels. By choreographing the release, the structure bleeds off the explosive kinetic energy of 25 million horsepower before it can damage the primary wall. Surviving the river's most violent cycles requires the structure to actively choreograph and bleed off floodwaters, serving as a precision throttle for kinetic energy. There is one final invisible threat to rigid concrete megastructures, and it comes from below: seismic activity shaking the earth. When millions of tons of rigid concrete are violently shaken by an earthquake, you would expect the rigid material to fracture and shatter under its own inertia. The solution lies in an engineering principle called dam foundation rock interaction. The dam isn't built as an isolated wall sitting on top of the dirt. It's calculated to function as a single connected system with the bedrock beneath it. When an earthquake hits, the structure utilizes a mechanism known as radiation damping. The unbounded foundation rock surrounding the dam acts as a massive geological shock absorber, bleeding off and diffusing the destructive seismic waves away from the concrete. At this scale, engineering requires treating the surrounding geology as an active, energy-absorbing component of the dam's defense mechanism, rather than just a resting place. A completed dam functions as a highly calculated active machine, locked in a continuous physical negotiation with its environment. Every element has a specific job. The exact geometry of the wall neutralizes the static water pressure. The bedrock absorbs incoming seismic vibrations, and the spillways actively tame the kinetic surges of floodwaters. By combining mass, shape, and geology, these structures operate as masterpieces of physics, holding an incredibly powerful force in a permanent state of mathematical checkmate.